Hi to everybody again. Welcome to this tech talk. Today is a pleasure to host, let's say, like this, Francesco Cariaggi. Francesco is I would say, more than senior machine learning scientist in PySchool, and it's also basically enjoyed PySchool from the very beginning, starting as a fellow, then as a coach for several years. We worked together on many challenges and European projects, and now Francesco is basically focusing his efforts on a project, on a European project, which is called Meetween. The project is about speech translation and speech foundational model. And so he's becoming very expert on that. And today he will tell us something more about how speech foundational models are connected, are related with large language model. And I'm sure it will be very interesting. I remind you that if you have any question, any doubts, these kind of talks are, let's say, informal, so feel free to really ask anything. Francesco would be more than happy to answer you and give you maybe some advice. I will leave Francesco maybe presenting again himself, maybe better than I did, and maybe share your screen, and so we can start.
Sure. Yes. Thanks, Chris. And so before I get started with the presentation, I'll say just a few words about myself, although you did a good introduction already. So as Cristiano said, I am a computer science. I have a degree in computer science from the University of Pisa in Italy. I joined PySchool over 4 years ago now, January 2021, after attending the School of AI program as some of you guys. And indeed, my current focus, I'm focusing my efforts right now on Meetween, this European project funded with 7 million euros that has a pretty ambitious goal of building the next generation of multimodal foundation models for speech, video, and text to power video conferencing applications. So hopefully by the end of the project, which is in 2027, you'll see some of these advancements, some of the outputs of the project inside some open source video conferencing applications. And what I'm presenting today is a paper that I worked on in the context of Meetween. This paper is a joint effort with among several institutions, and some of them are included here below, starting with Translated, PySchool, which I'm part of, as well as Fondazione Bruno Kessler in Italy, which is one of the top research institutions in the country. And this paper was accepted at Interspeech 2025 this year, so we're going to present it in mid-August. So yeah, I'm super excited to tell you more about our work. And the title is How to Connect Speech Foundation Models and Large Language Models, What Matters and What Does Not. You will see why this kind of verb was titled. So let's start with the motivation. So the motivation is all about like strategies for building multimodal models, especially for the audio domain. And one consolidated approach for doing this is to just take pre-trained components, in particular an audio encoder and a large language model, and then try to connect them somehow by means of this module that is referred to as an audio adapter, to make them interact, basically to get the most from both, and make the resulting model capable of new tasks. I just said that it's a consolidated approach because there's already quite a few works doing pretty much the same thing. We have Salmon, we have WAV LLM, 5.4 multimodal from Microsoft, quite recent. And so all these works just connect the pre-trained components with an audio adapter. But one key question, or at least two key questions, are left kind of unanswered. The first is how do you know, like, how each of these components impact the final performance of the model? And we don't know either, like, what empirical evidence supports the choice of a given audio encoder or a given LLM, or even an audio adapter. So like normally people say, okay, we take Whisper as the audio encoder, we take an MLP as the adapter, and we take LLaMA as the LLM, but they don't provide a rationale behind it. So the goal of this work is to explore different configurations for this complex model architecture, namely 20 different configurations, which are obtained by trying 2 different audio encoders, 5 different audio adapters, and 2 different LLMs. And the goal is to, again, assess the impact of each of these components on the final performance of the model, with a specific focus on 2 tasks, which are speech recognition and speech translation. So moving on to the model architecture, as I mentioned before, this is relatively simple. So you have a pre-trained audio encoder that is kept frozen throughout the training. You have a pre-trained large language model, which is also kept frozen during the training. And the only trainable part of the architecture is this audio adapter here that sits in between the 2 frozen components. This architecture is heavily inspired by LLaMA, which is an architecture that was initially conceived for the vision language domain. So LLaMA can do like reasoning and question answering, or this kind of tasks over both image and text inputs. Our model can do the same over audio inputs and text inputs, basically. So just a brief look at this architecture again. So you have your input audio here, which is passed through a frozen audio encoder. Then you get these red audio embeddings, which are then passed to this audio adapter, which does some operations over them, and tries to convert them in such a way that they can be ingested by an LLM. On a parallel track, you also have the textual prompt that instructs the model about the task it should perform. Here in this slide, you see that we're trying to do speech translation, and so we tell the model to translate the following audio from Italian to English. And then, as you see here, we are basically concatenating the text embeddings resulting from the tokenization and embedding of the textual prompt with the adapted audio embeddings. And then the rest of the architecture is just a plain LLM. So nothing really to comment on this. You already know how this works. Then moving on to the individual components, I said we tried different configurations. In terms of audio encoders, we tried 2 of the most popular audio encoders out there. One is SeamlessM4T v2, the large variant from Meta. and the other is Whisper Large V3 from OpenAI. In both cases, we only took the encoder part because, well, the decoder part we're not really interested in, and we are kind of replacing with the LLM. For the LLMs, we tried two different models. One is LLaMA 3.1 8 billion instruct from Meta. The rationale being that it's a popular multilingual model. And the other is Mistral 7 billion 0.3 instruct, which is a popular English-centric model. So with this choice, we also wanted to see whether, the fact that the model is multilingual has an important impact on the downstream performance or not. And then for I would say the juicy part, let's also look at which 5 different architectures we tried for the audio adapters. Just to refresh you a little bit on their role. Their role is just to adapt, as the name suggests, latent audio representations from pre-trained audio encoders to the latent space of an LLM. And they are made of 2 main components, logically. There is an optional length adapter, which tries to reduce the sequence length of the audio embeddings to approximate, let's say, the length of the corresponding textual transcription. You know that in audio you could have like different spans of silence. You can have speakers who speak with very different paces, So it may well be the case, for example, that, I don't know, like a 30-second audio corresponds to, I don't know, like 20 textual tokens. I know it's a bit extreme, but, it could possibly happen. And so the length adapter tries to reduce this gap in sequence length. And then you have the modality adapter, which maps the latent features that you obtain from the audio encoder to the domain of the large language model, which is the text domain. So let's see concretely which are these 5 architectures that we tried. The first architecture is a very basic one that involves no length adaptation at all. So you don't reduce the sequence length of the audio. And what you do is you just take the audio embeddings as they come out from the audio encoder, you pass them through n transformer encoder layers, and then at the end you get the adapted embeddings. Then the second architecture that we tried is a convolutional based architecture, which is similar to the base one, but also includes some strided convolution layers to reduce the sequence length of the audio sequence. In particular, you see that we have 2 convolution layer with stride 2, which means that the audio sequence is reduced by a factor of 4. So if you have like an audio sequence of 100 embeddings, after this adapter, you'll find 25 embeddings. Then moving on to the more advanced, let's say, architectures, we have this one that is based on an algorithm, on an approach that is borrowed from the spiking neural networks literature. It's called continuous integrated FIRE. This is interesting in that it, unlike the convolutional one, it doesn't perform a fixed fixed factor adaptation, but it performs a content-based length adaptation. So when I was mentioning before that your audio might contain, large spans of silence. Ideally, an adapter like this one would compress that silence into maybe like just one embedding to effectively reduce the sequence length and getting rid of unnecessary parts in the audio. How is this architecture? How does this architecture look like in detail? So again, let's suppose you have your input audio here, which you pass through the audio encoder. You get your audio embeddings here, the red ones, and then you pass them through the CIF-based compression. And what you get here is these alpha numbers, which are obtained by means of a convolutional layer again. And basically, they are like scores, if you will, that you assign to each of these red embeddings. And that kind of represent the amount of information, semantic information that is present in that particular embedding. And so you assign weights to each of these embeddings, and then you also keep track of the accumulated weights that you assigned to each of them. And when you reach a certain threshold, for example, 1 here, you fire an output embedding, hence the F in the name. So you fire an embedding, which is the weighted sum of the embeddings that you've found so far. So this would be like 30% of this, 50% of the second, and 20% of the first. And then you keep going similarly until your threshold reaches 1.0 again. Then you fire the second one, and then you fire the third one, and so on and so forth. When training this adapter, we also use 2 auxiliary losses. One is the CTC loss. If any of you is familiar with the speech recognition literature, you know what the CTC loss is. Basically, by adding a CTC loss in your architecture, you are trying to map a sequence of audio embeddings to its corresponding sequence of text embeddings. So the textual transcription. Okay, and the CTC loss, if you minimize it, what happens is that it makes it easier for the model to map the sequence of audio embeddings into the corresponding sequence of text embeddings. And since the SIF adapter tries to aggregate consecutive embeddings, this is important because with the CTC loss, you are trying to enforce a kind of monotonic alignment between the audio sequence and the text sequence. So, for example, you would say that the first 3 embeddings correspond to the first word of the transcription, and you say the second 7 embeddings correspond to the second word, and the last 3 correspond to the third word. And if your embeddings are organized this way, then it's easy to aggregate consecutive ones to get the target sequence. And then the other loss that you have is this quantity loss, which minimizes the difference in length between the actual target sequence and the sequence that you get from the SIF embedder or adapter. Then the following architecture is the CTC-based architecture. So CTC loss comes back again here. And just like SIF, this is a content-based length adaptation algorithm. So, depending on how your audio looks like, if it has a lot of silence, this this adapter will try to compress that silence. So yeah, let's see how it works compared to SIF. So just like SIF, again, you have your audio, then your audio embeddings. And then for each of these red audio embeddings, instead of predicting like a scalar value like in SIF, you predict a label, okay? You predict basically a token in the vocabulary of the LLM that you think that particular embedding corresponds to. So again, if we take the example I did earlier, if we believe that the first 3 tokens correspond to the first word of the transcript, in this case, nil, we will predict nil for each of these embeddings. Then the second 7 embeddings, let's say they correspond to the second word, mezzo. And again, for each of those, we predict mezzo. And the same for the embeddings corresponding to the third word. And then once we have these predictions, we can aggregate audio embeddings for which we have the exact same prediction and compress them into one. These aggregation is like I left it kind of abstract on purpose because you can implement it the way you want. You could do like a sum of the embeddings. You could do an average of the embeddings. You could have, I don't know, like an additional linear layer followed by a softmax that tries to predict the weights that should be associated to each of the embeddings, and then you take a weighted sum. You know, there's different approaches that you could follow. In this paper, we just took the average because we found it's the better approach. But in principle, you could use other ones. And again, of course, since this is a CDC-based compression, you have an auxiliary loss that is the CDC loss, which has the same purpose as in SIF. So to enforce a monotonic alignment, so that when you do this averaging or aggregation of consecutive embeddings, it makes sense because you know that the audio embeddings are arranged in a way that they follow kind of a monotonic alignment with the corresponding text transcription. And then finally, as the last architecture that we tried, we have the window level Q-former, which is another instance of a constant factor length adaptation. So what the window level Q-former does is it takes windows of audio from the input audio, and then for each window it outputs a fixed number of embeddings. In this figure here, you can see that for each window of 3 embeddings in the input sequence, we output 2 embeddings in the output sequence. And this number 2 is actually the number of trainable queries that we choose. This could be 1, this could be 2, 4, whatever, you choose it, and this determines the compression factor of the adapter. Now, as you can see here from this scheme, this is like a regular transformer decoder block where you have like a self-attention, cross-attention, and feed-forward. But the important difference is that the queries in the self-attention and cross-attention, no, actually in the cross-attention specifically layer, they don't come from the input sequence, but they come from a set of predefined and learnable queries. So, and the input sequence is only used as keys and values vectors. And well, as I mentioned earlier, this implies that the length of the output sequence is only determined by the number of trainable queries that you decide to use. So the window level Q-former adapter is inspired once again from a model from the vision language domain called BLIP2, where the Q-former is used in a much more complicated way because, well, as you see here, there are like a lot of other components to it. And it's used in the image domain. So, well, yeah, in the original paper, you have like a frozen image encoder. And then the Q-former tries to basically adapt the representations that come out from the pre-trained image encoder to the embedding space of the LLM with these learned queries that I described earlier, and self-attention, cross-attention, and feed-forward layers. In our case, as I just explained, we replaced the input image with an audio chunk, and we replaced the frozen image encoder with a frozen audio encoder. Then finally, we can move on to the results of this comparison that we run. We tested each of these 20 different configurations on Cobos 2, which is a dataset for speech translation and speech recognition from Meta. We only focused on the 5 main European languages, so English, French, Italian, German, and Spanish. And for the metrics, we used Comet for speech translation and word error rate for speech recognition. So before I dive into like fine-grained insights, if you will, I will zoom out a little bit and tell you what are the key takeaways. One, the choice of the audio encoder is the most critical factor. If you eyeball these results, I don't know if they're too small for you to see, but if you just give a very quick look, you see that whenever we use SeamlessM4T as the audio encoder, the performance on speech translation and speech recognition are much better than when we use Whisper. So this is the first highlight. And the second highlight is that there is no audio adapter that consistently outperforms the others, which, if you will, is a bit of a shame. Like, I think the paper would have been much cooler if we managed to, find that there is one adapter that always works best, and is, just consistently better than the others. But turns out there's no such thing. And instead, the best adapter really depends on the other components, so the audio encoder and the LLM. So first kind of fine-grained insight is that, as I mentioned earlier, SeamlessM4T is significantly better than Whisper in downstream performance. You see that on speech translation, SeamlessM4T beats Whisper by over 2 Comet points, which doesn't sound like a lot, but trust me, it is a lot. Like one or two Comet points implies a huge difference in terms of quality. And in terms of word error rate, again, you have over over a little bit more than 1 word error rate point, which again is a significant improvement. The second insight is that instead the choice of the LLM is not so impactful as the choice of the audio encoder. If you take, for example, the best results that you can possibly achieve with Mistral and LLaMA, you see that the difference is marginal. In speech translation, the difference is less than 0.2 comment points. And in terms of word error rate, same story. It's like around 0.2. So very, very marginal difference, which tells us that the choice of the LLM, although it does have an impact, it's not so crucial as it is for the audio encoder. Then the third insight is that it like revolves around the choice of the audio adapter. And you can see that the best audio adapter really depends on which LLM you choose. For example, if you choose Mistral as your LLM, then the base adapter and the window level Q-former adapter always rank first and second, and are kind of consistently better than the others. But if you use LLaMA, I mean, the story is a bit more complicated, because when you use LLaMA, window level Q-former is the best one when you have SeamlessM4T as the audio encoder. But then when you switch the audio encoder, things change completely, and instead the base adapter and the convolutional base adapter turn out to be the top performing ones. So again, this further highlights that there's no single choice for the adapter that outperforms the others. And then the final insight is that the content-based adapters, namely SIF and CTC, sadly, if you will, are consistently outperformed by the others. So again, if you just give a quick look at the results, you see that basically in every configuration, the content-based adapters are much below the other ones, even the base adapter, which is again surprising, because you would think that these more advanced approaches would make sense, especially when you're trying to bridge the gap between the length of the audio sequence and the corresponding text sequence. You would think this makes sense. It's sounds like a very reasonable approach. But then when you go and assess their performance, they are actually worse than the others. So why do these results matter? I will give you a few points from two different perspectives. The first is from a scientific perspective. These results matter because, as I mentioned at the beginning of the presentation, they give you an insight on which models or like which components to choose to build your multilingual and multimodal model composed of pre-trained components. And also, again, linking back to the last of the four fine-grained insights, these results challenge existing assumptions regarding the fact that the LLM might suffer from this sequence length mismatch between audio and text, because in our experiments, in our experience, this is absolutely not the case. If you look at the literature, you see a lot of claims saying, "Oh, it makes sense intuitively to try and reduce this gap," but again, nobody has ever proved that it's convenient to do so. And us, we actually proved that it's not worth it because the performance are worse. The second perspective that I would like to highlight is the business perspective. So why do these results matter from a business perspective? Well, first, these results tell you like what's the best trade-off between performance and serving costs across different architectures. Because you might think that different architectures, for example, those that try to reduce the sequence length as much as possible, such as the CIF or CTC, would positively impact the downstream serving costs, because if you have a shorter sequence that you have to feed to the LLM, then the inference time is a little bit shorter, and so you have lower latency. But as I was commenting earlier, this comes at the cost of worse performance. So it really depends on your use case and your needs. If you are willing to give up some performance points, then maybe you can use CIF and CTC as your adapter, because they make the sequence shorter. But if you're all about quality, then our recommendation here is don't use them and just go with more straightforward approaches. And yeah, that's already it. This was a short summary of our work. If you're curious, I invite you to read the paper. It's only 5 pages, because in interspeech and similar conferences you can only have 5 pages at most, so it's not like a long read. So if you want to dive deeper, I encourage you to read the paper. Thanks again for your attention, and if you have questions right now, I'm more than happy to answer.
Okay, thank you, Francesco. Thank you so much. So guys, if you have any, okay, Alessandro has some question, I think. Go ahead.
Yeah, so and when you talked about the CIF architecture,
yep.
So and you talk about also latency, but as far as I understand, so the CIF will shorten the length of the phrase according to how much content or semantic content it has. So it's kind of hard to. I mean, how do you measure latency in that context?
Yeah, that's a good question. So it depends. So you would have to have, I would say, specific test sets, which we haven't used in this work. But for example, if you have a test set made of audios that contain a lot of silence, okay, you might see the benefits of using a CIF adapter or a CTC based adapter, because if trained properly, these adapters would try and compress the parts of the audio that do not contain semantic content. And remember that whatever comes out of the audio adapters is fed to the LLM here.
Okay.
So you know that attention is a quadratic operation. So if this whole sequence is shorter, then the downstream operations are faster.
Oh, I see. Thanks.
Yeah, hi. My name is Ishan. So thank you for the presentation. It will be lovely to read the paper. So I just have a question. So when let's say we are improving the adapter on a domain-specific task or data, how much data would you typically need to improve the adapter?
You want to improve the downstream performance of the whole model on a specific task. Is that what you mean?
Yeah.
So how much data do you need? So in our experience, you don't need that much data, relatively speaking, because most of the heavy lifting is really done by the audio encoder and the LLM. If you train an architecture like this one, and you monitor the loss value over the training epochs, training steps, you will see that there are 3 stages. The first stage is when the LLM just freaks out and says, "Oh, what the hell are you feeding me with? Like, I've never seen these audio embeddings. So you asked me to translate the audio or transcribe the audio, but what the hell am I supposed to do here?" So you see that the loss is very high at the beginning. Then at some point, you'll transition to a second phase where the LLM kind of goes back to its previous state, where it can do language modeling. So it will output like coherent text, but it will not be able to follow the instructions that you give to it. So if you tell it to do translation of the audio, the LLM might instead do something else. For example, it might try to, I don't know, continue what is said in the audio, or provide some, I don't know, some insights, some comments about the semantic content of the audio, but it will not be able to do the downstream task that you instructed it to do. And then finally, you have this third stage where the model is actually learns to do the task, so speech recognition or speech translation. And you'll see that you will go through all these 3 stages within very early in the training. And then I would say like 10% of the training, you're already down to the 3rd stage. And then the remaining 90%, you are just trying to lower the loss a little bit. But all of this to say that if you can get to the 3rd stage, you already have a good enough model. And we trained these models with like hundreds of hours, order of magnitude. So I mean, this is not much. There are models that are trained on like tens of thousands or million hours of audio, but in our case, it was just in the order of hundreds.
Okay, thank you so much. Just last one question. Do you plan to train it on even smaller models, like using a smaller LLM or no?
Yeah, sure. That's a valid experiment you can do, yes. You could also try smaller audio encoders, for example. Yeah, totally. But I feel like, and it's also backed by the experiments we run, the choice of the LLM is quite important. Same with the audio encoder, as the results show. For example, so both Seamless and Whisper here are models trained for speech recognition and speech translation. So even if we just take the encoder part, the encoder part kind of already knows how to do speech recognition or speech translation, or at least it knows how to prepare the features
Right.
to do so. But as soon as we, for example, took a model that was not fine-tuned on speech recognition or speech translation, for example, this WAV2VEC BERT 2.0, if you go on Hugging Face, you'll find that there's also this model that is basically seamless, but without a speech translation and ASR fine-tuning. If you use that model, you will see that you can never go past the second stage that I mentioned earlier. You will always be constantly stuck in this second stage where the model behaves like a language model, but can never learn to do the task. So more than size, I would say what is important is how the model was pre-trained and fine-tuned.
Okay. Thank you so much.
Thank you for your question.
Okay.
Hello, Francesco. Thank you very much for your presentation. I know, like, do you think the prompt to the large language model, it will affect the final translations? And my second question is, how do you think we can adapt this model to run on some edge devices with embedded system, and also reduce the latency? Because I think many devices now, they would like to have this function like real time. I think maybe this research is not to generate real time translations and responses, but I just want to know what are the common techniques to make this real time. Thank you.
Yeah, thanks for your questions, Rui. So starting from the first one, that is a more than valid concern. And let me clarify one thing which I haven't mentioned. So during the training of these models, we didn't use a fixed prompt for speech translation and speech recognition. Here you see just one instance, which is translate the following audio from Italian to English. But what we did in reality was to train the model with several variants, several rephrasings of this same prompt to make it more robust at inference time to similar prompts. So for example, this is one, but sometimes the model might see, please convert this audio from Italian to English, or please perform the translation of this audio from Italian to English. So small rephrasings that make the model more robust to whatever prompt you use at inference time. And then the second question, so as you correctly said, this work wasn't much focused on inference performance, latency considerations. But so what I would suggest maybe to make this architecture viable for resource-constrained devices would be to look at maybe like two different directions. One is to reduce the model sizes, especially of the pre-trained components, audio encoder and LLM. You could use, I don't know, you could use like quantization, for instance, to reduce the memory footprint. You could do some kind of knowledge distillation to train a smaller variant of the model that tries to mimic the bigger one. You could use optimized inference environments like, I don't know, VLLM or SGLang, that kind of things. You could use more efficient implementations of the attention operation. Think about like flash attention or scale.product attention in PyTorch, this kind of things. This will all help to reduce the latency of these models. And then the second axis is like offline versus streaming. The autoencoders that we used in this work, well, actually, okay, let me say it. Whisper is not a streaming model by default. So you cannot do streaming inference if you use Whisper. SeamlessM4T v2 is technically a streaming model, because inside this conformer speech encoder, you have convolutional layers with causal padding. So you could technically use it in a streaming mode.
Yeah.
And then similar story for the adapters. For example, I don't know, here you have the convolutional adapter, which has convolutional layers. If you use causal padding here, but also in SIF, if you use causal padding here, this makes it a streaming model. And so you could reduce latency and make these models be able to operate in real time by maybe, performing these small architectural changes, and or selecting models that already support a streaming like SeamlessM4T and not Whisper.
Okay, thank you very much, Francesco.
You're welcome.
So, if there are other questions, we have still 1 minute. Will let me know. Okay, Vish.
Hey, Francesco. Nice talk. I was a bit late, so I missed some parts. I think I wanted to ask you, how much data does it generally take to benchmark, let's say, a model like Whisper on a specific downstream task?
So, okay, what do you mean exactly? How much test data you need?
Yeah.
Okay. Yeah, that's a hard question, because ideally you would like to test the model under different audio conditions. For example, I don't know, like noisy speech or clean speech, or different pronunciations, accents, this kind of variations. In our case, we only tested on Cobust, because it's one of the most commonly used data sets for this particular models. But I don't know. I mean, yeah, as I said, it's a hard question. I don't know exactly in terms of quantity how much data you need to reliably assume performance. But for sure, you would need more variety than just Cobos 2, which, if I'm not mistaken, is just audiobooks, or like, in general, it's like very low quality recordings from random people on the internet. So it might be that when using different data sets, these numbers change completely, and maybe see, I don't know, Whisper winning over Seamless, or a given adapter outperforming all the others. It's very possible, but we didn't do it in this work.
Understood.
Okay, thank you, Viju, Rui, Ishan, and Alessandro for all the questions. If there are no other questions, I don't know, Francesco, do you want to add something, or otherwise I would thank you for your availability and thank you everybody to being here, and I don't know, see you next time.